In section 8.1, we were introduced to the law of sines, which can be used to help us solve some oblique triangles. Unfortunately, the law of sines alone cannot solve all oblique triangles that we're going to encounter. So to use the law of sines, if I were to draw a triangle off to the side, so here's our triangle labeled. This is the type of triangle that we're going to solve. So when we're talking about knowing an angle and its opposite side, for example, if I'm given angle A and side A, that's a case where I can use the law of sines. But if we go back and look at the beginning of section 8.1, we saw that there were 5 types of oblique triangles that we were going to solve. There was angle, angle, side, angle, side, angle, and side, side angle. There are also side, angle, side, and the last one is side, side, side. So if we split these into two groups, then these 3 on the left-hand side, we can use the law of sines to solve these 3 types of triangles, because in all cases, you either know an angle and its opposite side, or you can find the angle and its opposite side just using the rule that there's 180 degrees in a triangle. But these 2 cases over here, for example, if I look at the side angle side case, that means that you know a side, the angle in the middle, and you know another side. But it's not this side that we know. It's 2 sides and the included angle between them. So in no case do I know an angle and its opposite side, so the law of sines can't work. And in this side, side, side case, we don't even know an angle in the first place. So for these 2 cases, we are going to use the law of cosines. So I'm going to take a moment to type this out, and then we'll work some examples that use it. Okay, so this is one expression of the law of cosines. So here's my triangle labeled in this way. So what this says is that if I take side C and square it, this is equal to a squared plus b squared minus 2 times ab times cosine of angle C. Now, we're not going to worry about how the law of cosines is derived, just like we didn't care about how the law of sines was derived. We want to see how to be able to use the law of cosines in an example solving an oblique triangle that the law of sines fails on. Now, this expression that I have here written in black is equivalent to this expression written in red. If you just solve this equation for cosine of C, you will get this expression down here. And the reason why it's maybe helpful to rewrite it like this is because sometimes the missing quantity we're looking for is a side, and sometimes that missing quantity is an angle. And we're going to use one of these 2 forms of the law of cosines in order to evaluate that particular quantity. You'll see when we get to working in some examples. Now, something else I want to mention, and if you look at this part of the law of cosines, this looks like the Pythagorean theorem. And that's not an accident, because the Pythagorean theorem only works for right triangles. That means that this angle right here is a 90-degree angle. If you ask yourself, what is the cosine of 90 degrees? Well, that's just equal to 0. And what's going to happen is, in a right triangle, with this cosine being 0, you're going to lose this expression right here, and you're just left with the Pythagorean theorem. So in essence, the Pythagorean theorem is really just a special case of the law of cosines. So let's back this up, getting unnecessary scribbles out of the way. And let's actually work an example. So this is the example that I want to work. And before I get started, I just want to mention that due to the limitations that I have on space on this whiteboard, what I'm going to do is I'm going to do my evaluation below this line. And once we find a quantity, I'm going to clear this space and we can go back and find the other quantities that are missing. The full example is provided in the PDF that accompanies this video that's also on my courses. So in this problem, we see that we know side A, side B, and angle C. So it's two sides and its included angle. So this is a side angle side problem. Now, what I'm going to do first is I'm going to find this missing side. Because notice that if I want to get C, this says C squared, but I can find C just by taking the square root of both sides. So this is square root of A squared plus B squared minus 2AB cosine of C. But I know side A, side B, and angle C. So I'm just going to plug those values in. So this will be 25.4 squared plus 73.8 squared minus 2 times those values, 25.4, 0.4, 73.8 squared times the cosine of 22.28 degrees. So all of this I want under the square root sign, so I've got to extend it. And now I just wheel out my calculator, and this is going to give me that C is approximately equal to 51.2, and my units of measurement are the same as it was for the other sides, so this is going to be in centimeters as well. So we're going to come up here, and in red, we're going to put 51.2 centimeters. So now we have all the sides. Now we've got to go back and get the two angles. So let me clear this bottom part of the screen and we'll go back and get, let's say, angle B first. If you go back and look at the PDF, you will notice that I have that all three forms of the law of cosines is written out, depending on which side of this triangle that you're trying to find. So for example, I'm trying to find angle B. So what I'm going to do is I'm going to use this formula right here, but I'm going to rewrite it in terms of angle B that I am looking for. Now, that's going to look like this. Cosine of B is equal to, now notice how these sides are listed. This is angle C. So side C squared is the quantity you're subtracting. The other two sides, their quantity squared is what you're adding. So this is going to be A squared plus C squared minus B squared divided by 2 times the other two sides. Like this was angle C, we used side A and side B. Side C was not part of this denominator. So I'm going to say divide this by 2AC. So even though you're not going to have to memorize the law of cosines, because if you'll look at your identity sheet, the law of cosines is at the bottom, but you will need to know how to rewrite a given law of cosines in form of something that you need depending on which quantity you're looking for. So this expression right here only uses the sides, and I know all three sides. So I'm going to plug those values in. So this is going to be 25.4 squared plus 51.2 squared minus 73.8 squared divided by 2 times 25.4 times 51.2. And this is going to give me approximately negative 0.8381. So what this says is the cosine of angle B is negative. If that's true, angles of triangles are only in quadrants 1 or 2. You can't be in quadrant 3 because then the degree will be more than 180 degrees. So since we're dealing with angles of triangles, we're stuck in quadrant 1 or 2. And if I tell you that I'm thinking of an angle whose cosine is negative, I have sort of told you that we're looking at a quadrant 2 angle because the cosine is positive in quadrant 1, but negative in quadrant 2. So what I'm going to do is just take the inverse cosine of this number over here. So negative 0.8381. And since angle C is in degrees in this problem, make certain that your calculator is in degree mode for this. So my calculator comes up with, to 2 decimal places, 146.94 degrees. And that is angle B, 146.94 degrees. Okay, now the reason I rounded the angle B to 2 decimal places is because I took the cue from the given angle that was provided to me. Angle C was written to 2 decimal places, so I just kept the same number of decimal places for angle B as well. And I'm going to do that for angle A too. Now I have 2 ways of finding angle A. There's a long way and a short way. And it's not like one is difficult. One uses the law of cosines. But if you know 2 of the angles, you can just take 180 minus angle B and angle C, and that will tell you what angle A is. So let's clear this at the bottom, and let's find angle A. So what we're using is that angle A is 180 degrees minus the 2 angles that we know, 146.94 degrees minus 22.28 degrees. And this is going to give us a value that is 10.78 degrees. Now this is a small angle, but it's positive, so it's still a valid angle, still a valid value for angle A. And this is the last remaining quantity, 10.78 degrees. So we have solved this oblique triangle, but we only needed the law of cosines 1 time. I never used the, we used the law of cosines twice, one to find side C and one to find angle B. But once I know 2 of the angles, getting the third one, you will always see me just take 180 minus the 2 known angles. Okay, so the next example that we're going to look at is not even going to give us an angle at all. It's going to give us all 3 sides, and we're going to have to find all 3 angles. So I moved the solution over here off to the side to give myself some more room to write. So let's assume that our problem, the 3 sides that we're given is 16 meters, 20 meters, and 32 meters. Now, it is clear that this is a side problem. No angles are provided. So it really doesn't matter. It does not matter which angle you start with, but you can't use the law of sines because you don't know any angles. So you can't know an angle and its opposite side. So let's find angle A this time. So I'm going to rewrite this expression so that it's cosine of A. So pause the video right here and you write it down and then check it against what I'm about to write. Okay, so we're going to use cosine of A So the thing to remember is that the side you are subtracting is the side opposite the angle in this cosine. So since it's angle A, you know that you're going to have a minus A squared here at the end. The other two, it does not matter what order you put them in. B squared plus C squared minus A squared. And I'm going to divide this by 2BC. Notice the denominator does not use the side opposite the angle that's in the cosine. But this expression right here on the right-hand side only uses sides, which is handy because that's all I have. So cosine of A is going to equal B squared plus C squared minus A squared divided by 2BC. Now notice that I'm not writing the units in here. That's fine. So I know that I'm just going to pick either degrees or radians. So let's say that we're going to be evaluating this using degrees. So this is going to come out to approximately, actually I don't think it's approximately. I think if you put this into your calculator, you actually get equal to 0.9125. So look at what this line says, that we are trying to find an angle whose cosine is positive. That means that this is a quadrant 1 angle. So I expect my answer for angle A to be somewhere between 0 and 90 degrees. So angle A, the way you get rid of this cosine is you just take the inverse cosine of this number right here. So angle A is inverse cosine of 0.9125. And if your calculator is in degrees, you should get approximately 24.15 degrees. Now, I'm taking it for granted that you are following along in your calculator and that you're verifying that these numbers are correct. Because when it comes down to being able to type these into your calculator, you're going to need to know how to do this cold. If I give you an expression, you don't want to have to do all the work correct, but get the answer wrong because you typed it into your calculator wrong. So 24.15 degrees is my measure of angle A. Now I'm going to do the same thing for angle B and angle C. So let's take a moment, let's clear this, and we'll find, let's say we find angle B next. It appears as if I have lost the recording of the explanation that I had written, but what this picture shows, and I'm not going to go through the details again because this is primarily just a rule from geometry. If we look at the length of this red line, this is 17 yards. That is side A. But these two blue lines, the sum of those two lines should be longer than 17. I'm sorry, should be longer than 17, because the shortest distance between point B and point C is always a straight line. That's the rule from geometry that I'm using here. But if we look at the length of this blue line, it's 1.5 plus 15.4. That is 16.9 yards. That means that the blue line here is shorter than this red line, which is impossible. So even though we do have a rationalization from geometry of why this has no solution, let's see if we can't get the law of cosines to back us up on this. So all the notes that you see written here, apparently I was not recording when I was making those. So let's remove them and let's just verify for ourselves that there is no solution to this triangle. Let's try to find angle A. Okay, so we're using this formula, and cosine of A is equal to 15.4 squared plus 1.5 squared minus 17 squared divided by 2 times 15.4 times 1.5. This comes out to approximately negative 1.0733. Now, what I would like you to do is pause the video for a moment and try to look at this line right here and ask yourself what is wrong about this equation. So what is wrong with this equation is, what do we know about the cosine function? Think of its graph. So here is plus 1 up here, and here is minus 1. If you look at the graph of cosine, it starts here at positive 1, and then it drops down to negative 1, and then back up to positive 1, and then it just keeps oscillating between positive 1 and negative 1. But it can't get outside of this boundary. It can't get larger than positive 1. It can't get smaller than negative 1. But what this says is that angle A has a cosine value that is down here at negative 1.0733. This is an impossible value of the cosine because cosine is locked between negative 1 and positive 1. This is the range of the cosine function. So it's impossible to get the cosine value to give me a number that is less than 1. Just as it's impossible to get a cosine value that's bigger than positive 1. So if you ever get a number less than negative 1 or a number greater than positive 1, that cannot be the value of the cosine or the sine for that matter. So with this statement right here, because this is an invalid value for cosine, so invalid value for cosine of A, that means there is no solution to angle A. And if there's no solution to angle A, there can't be anything for B or C, because you don't even have a triangle if you don't have 3 angles. So sorry if this last example is a little messed up, because I apparently forgot to click record when I explained it the first time. But all the information is here, and I hope I've done it some type of justice as far as explaining why this triangle has no solution. If you have any questions, please reach out to me. This is going to mark the end of the test 3 material, and test 3 will cover section 7.4, 7.5, 8.1, and 8.2. Then we'll deal with section 8.3, which I believe is complex numbers. But for now, let's focus on the test 3 material. Reach out to me if you have any questions.